All right, so today we're going to talk about main memory. Today lecture and next 3 lectures, which are again main memory and virtual memory. They are kind of related, and try to. We're going to take it a little bit slower. So if you have any question or something, stop me during the lecture so we can go back and forth. That makes it easier not to confuse anything. All right. So. Oh, I gotta click on it. Okay. So we talked about chapters from 1 through 7 from the book, and again, these were covered in your midterm 1. None of these are gonna show up in midterm 2. So from now on, you can basically make sure that you catch up with the class and do better in your midterm, second midterm. So, and again, I asked you to, email if there's anything you want for your groups, and also you were supposed to have a good break. So this is real because I actually got one feedback. So I try actually to put the deadlines, not through the weekends. I understand that the weekends are, big chunks of time for projects. But on the other hand, I don't want to ruin, the weekends or, spring breaks, for students. So I'm going to actually warn you ahead that, hey, the time is tight, so start earlier. But at least, after you submit, your project, then you can enjoy your weekend or, your break. Okay? So this is just like 2 ways of doing it, I guess. So today we're going to talk about main memory, how memory allocation works, fixed and dynamic, and we're going to talk about fragmentation, what is that, and what is the difference between external and internal fragmentation, address binding, and hardware address protection, how hardware is actually helping out the operating system with memory protection, and paging and segmentation. We're not going to cover all of it. Some of these and basically, the more details of them we're going to talk about on Thursday, next session. All right? So the first thing is, if you remember, the memory management is a part of one of the main roles of the operating system. So operating system comes here and runs on the computer so it can share the resources of the computer among different processes, right? Different processes want to use CPU, so we have a scheduling for that. We have already covered that. One of the main other things that processes need is memory. They want to load on memory, they want to use memory, and they have data, instruction, whatever. And the operating system role is to manage it. First of all, when more than one process should want to occupy the same space of memory, how do we manage it? How do we fit? Because it might just be more than what we have, right? That is one thing, and how we can keep them separate so that the different processes don't access each other's data or modify it. So that is again another thing. So one of the things, for example, is that if you have like limited memory, then we have like backups, right? So we have main memory, and then we have hard disks or magnetic disks, right? Or what is there's also another issue with accessing memory and hard disk, which is like too slow. So on the other hand, we have like closer memory, like registers and cache, which CPU can directly access. So up to here is not much of a concern to operating system, relatively again. And but when operating system again is responsible for moving data between the levels, right? So now, one of the, again, main job for OS is allocating memory to processes, right? So when a process wants to load, how to put it on the, physical memory. So that's called allocation. When we have like a, space, and then the operating system wants to allocate some of it to a process. When we don't have a space, that's another issue, right? So one of the ways is just like very simple, is divide memory into fixed size partitions, and then just like give partitions to processes, right? So, it's just like, this is your memory, and then it's just like equal chunks, and then, OS itself like gets a chunk, and then one process for each partition for one process. And we're assuming like each partition is enough for a process. So, the problem arises that the degree of multiprogramming is bound by the number of partitions, right? Because that's just like the number of processes. And it's just also the limitation of that partition size that, dictates how, like, large can a process be. And the other problem is the internal fragmentation. This is an important term. So it's probably going to show up in a quiz or exam or something. Internal and external. So internal fragmentation is when allocated memory is larger than the requested memory. So one issue is if the process is larger than the one partition, what are we going to do? The other issue is what if the partition is larger than the process? If the process is too small and we allocated a whole partition, then we're just like wasting a lot of memory, right? So this is the example. So this is the allocated memory to a process, not the whole memory. But then, the process may use just a little bit of it, and then the rest of it, because again, it is allocated to the one process, it's not going to be used by anyone. So this is called internal fragmentation, right? So another way is to do it dynamically, right? Variable length, right? So we have the memory, and then we assign each process only, how much they need. So this process is smaller, this process is larger, we're going to allocate different sizes, right? So the problem is now we're gonna have a lot of holes. That's like what we call them, block of available memory, right? So we have different processes and then available holes in between. Now we have various size holes, and then now different processes want various size memories. How are we going to fit those into those, right? Now that is. First of all, operating system, because it's not all fixed size, so the operating system should, keep track of all the allocated partitions and their sizes, where they start, and also the free partitions or the holes, and so they, later on, if a new process wants to load, then the operating system can figure out where it fits, right? Now, also a problem is external fragmentation. External fragmentation is because, when we have the actual memory in total, but we don't have a big enough, block to fit one process in. So this is an example. We have enough memory, as you can see, but we can't just allocate one process into it, right? So this is called external fragmentation. And the rule of thumb is maybe, we can lose 50% of the space. So one way to do that is by compaction, and that is, moving things around a little bit. But that only can happen if you can do it at execution. Like when a process is on memory, how are you going to be able to move it in somewhere in memory without, altering its functionality, right? Well, a lot of the modern operating systems actually do it, at execution time. They are capable of this. And again, some of the concepts that we're talking about are not actually how operating systems like, Linux or Windows work. But these are simplified concepts. All right? Any questions so far in the allocation? All right. So, again, when we want to fit processes into, blocks of available memory or holes, there's different algorithms. One is first fit. So we're going to look at the list of the holes from the, starting of the available memory, and then we look at different blocks. All right, can I fit this process into this block? No. Can I fit into this block? No. Can I fit into this block? Yes. All right, that's it. That's first fit. And then the best fit is we allocate the smallest hole that is big enough, right? So we're going to basically check our new process to all different, available blocks, and then we see, okay, among the blocks that we can fit this process in, which one is the smallest? So we lose the, slightest available memory in that block. So this is called best fit. Worst fit actually has the opposite approach. It says, okay, among the holes that we can use, which one is the biggest? Because that way, we're not going to lose a slight available memory. We're going to be left over with another useful block. So the approach is kind of different, and to be the naming suggests that this is actually worst and this is best, but it's not that's clear. So there are cases that first fit is better than best. Sometimes it's opposite. it depends on the example. You can find really, examples that the worst fit actually is best. But, generally, first fit is faster because you don't have to go through all the, available blocks and search for them. And then best fit is better, again, in terms of utilization, generally, on average, maybe. And worst fit may lead to less fragmentation because it, leaves available blocks. Yes?
Why is this not sequential?
What's that?
Why is it not sequential?
Because processes come and go. Right? So when a process goes, then it will leave memory. So that's a good question. But so this example is like this, right? Process 5, 9, 10, and 2. Now what if process 9 finishes? It will leave and then it will free up its memory. So now we're going to use that. Yes?
Does allocated memory for processes have to be contiguous, or can you split it up?
We're going to, again, not necessarily. We're going to talk about it. So this is a simplified version, which we're considering, they're contiguous. All right? Any more questions? So this is an example of given 5 memory partitions of, different sizes. How would you, each of you, different algorithms, and what you're going to do at the end of the lecture, we might have time, and then you do it on the blackboard. Otherwise, you just list them, and then just run the algorithm one by one for each of the processes in order. If it's the first fit, you take a look at this size of the process. Okay, so does this fit into this? No. Does this fit into this? Yes. That's it. First fit does that. And then we will end up with a 288 block of available memory, a whole, right? Because this is going to take 212 kilobyte of this, so we're going to end up with another 288 block. And then that again, you should check, for example, this into this, then into that, the 288, it doesn't fit. We're going to take a look at that, right? So, address binding. When you write a program, you never use any addresses unless you actually are, programming in assembly language for something like for bootloader or something. You never deal with exact addresses. You have symbolic. And then the compiler binds them into relocatable addresses. Again, because the compiler does not know at runtime where is it going to be on your memory, right? You can ask a compiler to do this. You can ask a compiler to, fit this, symbol exactly at this address. And the compiler does it, and then when you load it, it will load it into that address. Otherwise, they will be relocatable. So, for example, wherever the count is, it's going to, replace it with 100 bytes from the beginning of this module, because the compiler does not know where is it going to begin. Yes?
I've seen some assembly volatile code. Is that where you would see that?
Volatile and non-volatile is different, but that has to do with optimization of compiler. Yeah. I mean, there are other probably characteristics of it, but most use of volatile is when you're dealing with hardware programming and you don't want optimization. So, and then the loader binds those relocatable addresses to absolute addresses. So when the program now wants to load, it realizes, okay, I want to load it at address 1,000, so this will be at 1,100. Next time, if you load the same program at 2,000 address, then this will be, bound to 2,100. So this is what's going to happen at load time when the process, the OS is loading a process into memory. Okay, and then when it is there on memory, it's you can consider them to be absolute. Again, there are things that are not that straightforward. For example, when you have dynamic libraries, when you have on-demand or dynamic loading. So a lot of the time when you have a gigantic program, the operating system does not load all of it into memory. It load because some of the code actually is not supposed to run. For example, an error code. When you are capturing an error, you don't expect that to happen. So, that subroutine is not expected to, so if you just load it onto memory, you're just wasting memory. So a lot of the time, you have dynamic loading, where you actually load the main part of your program, but not all the routines. So when you want to call a routine, then it checks that routine is not available on memory, then it will load that routine somewhere in memory and then, replaces it with absolute address. So a lot of things can happen, at runtime, but, a general thing, this is like address binding. And now each binding is a mapping between address spaces. So what is an address space? Address space is whatever address that you observe and can use. So a typical x86 program considers that, I have addresses starting from 0 to 2 to the power of 32 minus 1, and that I have all of it. Because that's the way the computers were designed. The 32-bit architecture was built without operating system in real mode. So when a computer, just like the CPU, kicks in, you can have one program loaded into a memory, and then again, if it's a single program, it has all the available memory. So from the perspective of the user program, the address space is that. But we have, as we can see, when the operating systems comes, there are different address spaces. So what we call this logical address space is what the user process and the CPU sees. So let's say you have only 1 gigabyte of memory. Physical memory available on your computer is 1 gigabyte. The user program does not know that. The user program thinks, again, that, okay, I have from 0 to 2 to the power of 32, negative 1. I have it. That is the logical address space. Now, again, each process thinks that they have that, but you have 100 processes running. Each of them thinks that you have 4 gigabytes of memory. Obviously, that's not going to happen, right? And obviously, not all of those processes are going to use that much memory, right? But the problem is that you cannot just map your physical memory to user memory. First of all, what if a user process wants to use some portion of the end of memory, right? Well, you don't have that much memory. Even they totally want to occupy maybe 2 megabytes of memory, but maybe they want to allocate something at the end of your memory. Well, you don't have it. What if 2 different processes, they both want to use the exact, 1 megabyte in their logical address space? You cannot just map it into your physical space because they will collide, right? So there's a mapping. So the simplest way for an operating system to map, again, this is just very simple, is that we consider, again, the process to be contiguous, and we have 2 registers, base register and a limit register, right? So when a process is only using, 4 megabytes of memory, their limit is 4 megabytes, and they can address between 0 to 4 megabytes, but it's not loaded actually from 0 in your memory. It might be loaded at this address, right? Operating system is loading this process at this address. So the process doesn't know this, but the operating system does. So what the operating system does is that it checks the process and then knows that, okay, this process wants 4 megabytes of memory, and it is only supposed to use between addresses 0 to 4 megabytes, right? So I'm going to look for an available, hole in the memory space, and okay, I found it here. I'm going to load the process into here and then set the base register for this process at this number. So this is going to be in their PCB. Again, part of the process control block, which is not accessible by the user process itself, but the operating system can. So when the operating system is scheduling this process, it will load the base register and limit register of CPU with these numbers. So this is basically where hardware is going to help it. So again, remember, this cannot only happen in software, because once the operating system hands the execution to the user space, there's no guarantee that this process is not going to access the 5 megabyte address, right? The process might do it by mistake or deliberately. So how can we protect the other process from the access of this one? This cannot just happen in software. We need hardware support. For that, MMU comes here. So the MMU indirect all the accesses at hardware. So what it does is when a user process says, okay, I want address number, like, the first megabyte of my memory, at hardware, it will add that address to the relocation register, the base register, and then gives the user whatever is on physical memory. It's like, again, in indirection, I don't know, maybe an example would be in library. You want, the third book of biology, but you don't know where are them. You just let the librarian know, and then they know where the biologies start. They're going to pick the third one, bring it to you. Right? Kind of it. So, again, the relocation register or the base register is what is loaded by the operating system when the context switching is happening. So, because, again, base register and limit register, both of them, are unique to each process. And so when CPU wants to access one address, that is going to just like add it to the base register, and the actual physical memory address is going to go on the memory bus. Okay? So again, the user program, what the CPU tries to access to the MMU, they don't know anything about the real or physical addresses. It's just like logical. Alright? So again, this is another diagram of the protection. So there are two things happening. The first is adding of the base register. Second is checking with the limit register. So if the process is only supposed to use 4 megabytes, if they try to access anything beyond that, who's going to check that? Again, the hardware MMU. It checks at the base, either it's not exactly like this, but the concept is the same. So it checks if it's like accessing beyond its limit. Either before adding the base, it can check with the limit, or after adding the base, it basically, checks with the base plus limit. And if it's, if it's within that range, it tries to access it. Otherwise, it does not access, it does not dereference that memory. It traps into a memory access. Just forgot the interrupt name, right? But in your Pintos, actually, it's in the, you're going to use it in the user program. If a user process tries to access something which is out of its available memory, it's either not mapped, it's not either not allocated, or it's out of bound, dereferencing null pointer or something. It's going to trap into the operating system. All right. Any questions? No, nothing. Okay. So let's go. Now we're going to go for being non-contiguous, because the physical address space a process can access is not necessarily contiguous. Like, it's not that that simple because of the fragmentation errors. For example, what you're going to do is you're going to instead of having processes like this and then having fragments between them. And again, this was a simple one, which is either dynamic size or just fixed size. We're going to get a little bit real. So what we call paging is when we have fixed sizes, like the first example, but not like that big partitions. These are actually very small partitions. These are from 1K to few megabytes, right? And it's so basically not each process is not given only one page. They get as much as they need. So this is to help the mapping between the logical address space and the physical address space, right? So what you're going to do is you're going to divide the logical and physical address space into equal chunks. Let's say 4 megabytes. Your physical memory, let's say it's 4 gigabytes, it's going to be divided to 1,000 chunks of 4 megabytes. These are called frames. Your logical space, which is 4 gigabytes also, is going to be also divided to equal size pages, right? And basically your physical memory and your logical space, they don't have to actually match the same size. So let's say you have 2 gigabytes of memory, so you have definitely less frames than your pages. So you're going to keep track of which frames are used and which frames are available, and then you're going to match pages to frames. So you're going to say, okay, this page is going to be mapped to this frame, this page is going to be mapped to this frame, and so on. So by doing this, the operating system will have a page table for each process. You remember, each process has a different logical address space. 4 gigabytes for each process. But they're not going to use it. So the amount that they're going to use it, those pages will be mapped to separate frames. Maybe this process is only using 10 pages. Now this process is using 20 pages. The other process is using 15 pages. So total you have, 35 pages? 45. So 45 frames you have available. But now there is no need for any colliding, because you're just going to assign different frames to different pages, and then each process have a page table that will tell, okay, page number 5 of this process, which frame is it? Alright? I'm going to take a look at that. But because, again, we are giving it a fixed partition size, when we assign one page to one process, not necessarily the whole page is going to be used. So the bigger page, the more internal fragmentation you have. The smaller page, you have less waste of memory in the fragmentation, but because you now, instead of like 1,000 page, you have 10,000 page, you have a bigger page table to assign frames and pages, right? So that mapping itself takes, a table on the memory. So it's a trade-off. The smaller you make the frames and pages, the more number of frames and pages you have, and the more, mapping you have to deal with, the bigger the table you have. The smaller the number, the larger the size of each frame and pages, the easier the page table handling, but you'll have more fragmentation. Okay? So, now, when you have like page address translation, again, that is the page table. So you have a page table, and when you want to address one logical reference, you remember, the CPU only references logical address space. So when the CPU wants to address this address exactly, it's going to be divided. Okay, which page is it in? And within this page, what is the offset? Right? It's going to be separate. And it's actually be very easy, because it's just going to be chunks of binary number, right? You're going to divide some part of the, high bits. That's going to define the page. The lower bits is going to define the offsets. And then the page is going to be mapped to the frame using the page table, and the offset is going to be the same, because you remember, if this page is mapped to this frame, the first byte is going to be different. But then, the 100th bytes within this page is the 100th byte in this frame. It doesn't matter. So let's take a look at this example. So when a CPU addresses a logical, address, it's going to be divided. The higher bits are going to basically define the page number. And let's say this is 32 bits. We have 4 bits, the 4 highest bits, which can go from 0 to 15 to page number. So, and then the lower 28 bits is going to define the offset. Now, the offset is going to be the same, because that's, again, the size, each frame and each page has the same size. So their offsets can exactly vary to 28 bits. But the page index is going to, reference to the page table, and then it's going to be shown, okay, this page is this frame, so that frame is now going to be in the physical address. So then that address is going to be, used. All right? So that's address translation. Is that clear? Good? All right, let's move on. So this is an example. So in the logical memory, let's say we have like 4 pages using, this process is using 4 pages, and now we have this page table. Page 0, 1, 2, 3 is mapped to frame 1, 4, 3, 7, accordingly, right? So this is going to be how the memory how is like we're looking at it. So these are the frames. Frame 0, 1, 2, 3, 4, 5, 6, 7. We have like total memory more than what this user process uses. And page 0 is going to be mapped onto frame 1. Page 1 is going to map to frame number 4. Page 2 is going to map to frame number 3. Page 3 is going to be mapped to frame 7. Okay? And the process does not know any of it. That's the whole purpose of it, right? The process only sees this, and then we're going to do this with the hardware. All right? So, and one more example. So let's see. We have all these are not pages anymore. These are exact, let's say, memory addresses. So from 0 to 15 with characters A to P, this user has on its own memory. And in this case, each page is only 4 bytes. So this is 1 page, it's 2 page, 3 page, and 4 page. So when you access, and this is the page table, the same goes with the physical memory. These are exact memory addresses, right? So 4 bytes for each page, 4 bytes for each frame. Now, when we address, for example, this, let's see how it's mapped. So let's take 9. The address 9 is 1001, right? Because we have 4 byte pages, that means within each page we need 4 addressable memory. So we need 2 bits. So 2 bits define the offset within each page. Then the rest of the bits, which are again 2 bits, are going to define the page index. So in this case, when we have 9, 1001, actually I may be able to just put it off a little bit. Not too much time though. So 1001. So this is going to be offset, D or offset. Then the 10 is going to be P or page number. So 10 is 2. 10 in binary is 2. So that means it's going to be on page number 2. We can also see it obviously, right? Page 0, page 1, and page 2. And what is the offset in page 2? 0, 1, which is 1. 0, 1. So the address that we want to address, 9, is on page number 2 and offset number 1. And now looking at the page table, page number 2 is mapped to frame number 1. Frame number 1 is 0 and then 1. And then adding the offset, so J should be right here. Right? So then obviously the whole pages are mapped. So this page is all mapped to this. Because this is page 0, 1, 2, it's mapped to frame number 1, 0, 1. This page is 0, 1, the whole page is page number 1, it is mapped to frame number 6, 0, 1, 2, 3, 4, 5, 6. Right? So, now, the operating system should take care of the free frames, right? Because the processes know their own pages, basically they address, and now when we're going to use, when we're mapping all the pages of this process to some frames, pages of this process to some frames, pages of this, do we have enough available? When a new process wants to, come, how are we going to map its address space? So the operating system takes care of it by, keeping track of all the free frame. So let's say we have all these frames available, and now a new process wants 4 frames because it has 4 pages. So it's gonna allocate a new page table to the process, and it's gonna assign some of the frames, so 14, 13, 18, 20, and now it's gonna only have 1 free page here, right? So now if a new process comes and it has 2 pages of memory, we cannot fit it. This is how the operating system now works. Alright? So some of these, you have to understand them. I'm not sure if you're going to need them in project 2, but definitely in project 3. As well as virtual memory, which is next week. Alright? So how are we going to do with shared codes? So when we have, different pages, it's easy because you can have some code on a different process, you map it to the same pages of different processes. So in this example, let's say you have the window systems, meaning, the window that you have, like, X as close, minimize, or, maximize, whatever, those are routines that are written by the system, but can be used by all the processes that has this window, right? The same code will run when you hit exit mark, right? So how is that possible? So that it doesn't make sense to copy the same code for each process on memory. That's a waste of space. So we're going to share code. So that's going to that code is going to be somewhere on memory, and that code will have the same location in the logical addresses of all these user spaces. So all of them will map to the same physical address. The same code will run for all of them, whenever you hit the exit mark, right? And then each of them, obviously, they're going to have their own private code separately, which is, again, for their own, no other process can access, because this was specifically, made shared. Operating system takes care of it. Let the other processes, access it, manages the page table and everything, make sure that their access is read-only, for example. But whatever that each process has for their own, it's going to be only in their, page table, not mapped to another user process's logical address space. All right? Any questions for paging? We're going to talk about paging again tomorrow, next session, in detail, because paging, you have you need examples, and we actually have multi-level paging, and so we're going to talk about that in depth. Okay, I thought that there's a question. All right, so next, this is an example for shared pages. As I said, you see, each process has the ED 1, 2, 3 as part of their logical address space. They have their own data. So this one has data 1, this one has data 2, and this one has data 3 separately, right? So on memory, we only have one ED1, one ED2, and one ED3, because it doesn't make sense to just copy the whole thing. But separate pages or frames are allocated for, each process, right? So now in their page table, these pages are allocated to the same frames, 346, 346, 346, but they're going to also have their own private data separate, not accessible by the other processes. Okay? Now, one thing which is obvious is that a program itself does not consider its own memory, logical address space, in a array of bytes. A program doesn't just consider, or a programmer, let's say, doesn't consider, okay, I have, I need 4 megabytes because I only need these bytes and these codes, instructions. That doesn't work like that, right? You separate them in separate modules, right? So you think that, okay, I need a stack separately, and then, maybe I need some space in that, maybe 1 megabyte, whatever, but then you think of it not interleaved or exactly, stacked to another module. So your symbol table, your main program is separate, your routines are separate. The programmer think of it as modules. Now, one way to actually map is the same thing, to consider the separate modules as separate chunks. Right? So that's called segmentation. So we consider each of these as segments. So we have a code segment, we have a data segment, we have extra segment, and CPU also has these registers, like x86, for example, has these registers. And now that depends, you can move different segments at different parts of memory. But again, each segment is for its own because they're related to each other, let's say, right? And now segmentation is that one scheme that you can have the segments mapped to the memory, and you can have each segment separate, for your, different objects or procedures, whatever, And how you can now take care of this is by this. You map different segments at different parts of memory. So this looks like our first example, which was various size, but now this is not different processes. These are all one process, but different segments of one process. Okay? Now, instead of a page table, because pages were like kind of easy to understand, right? These are like exactly fixed sizes, and we only need to map page index to frame index. In this case, these are not fixed sizes. Segments can have different sizes and be mapped at any location. So instead of like a page table, we're going to need a segment table. So in order to handle segmentation, the operating system will actually consider the addresses as segment number and offset, right? Kind of again the same idea of having a page table, index and offset within the page, but this now we have like segments. So the segment table instead of page table now has two dimensional information. One is the size and the other one is offset. The offset was the same in page, but because now we have various size segments instead of fixed size pages, we also need a size for a segment. So we call them again like base and limit, right? So when we have like this segment in the logical space, it has it has a limit, and now how we map it to another location on physical memory defines where the base goes. But the same size will still be occupied on physical memory, right? So now we have two registers, which is the segment table base register, another one which is segment table length register. There are similarities again between segments and pages. Just make sure you understand both of them. So the segment table points to the segment table's location in memory. So if the user program wants to access its code segment with the offset of 1000, the code segment is mapped to a different base on physical memory. And the offset is going to be the same, so we're going to just point to the 1000th offset within that segment on physical memory. Okay? So, and how are we going to again check that we're not, going over the allocated space for each segment is this exact way that we did, as before. We have a limit register, and the hardware checks that, the offset that the user program is trying to access. Is it within the range or not? Okay? So let's take a example here. So here, the CPU is now trying to access a memory address, logical. Part of it is the segment index, part of it is the offset. Now, the segment index goes to the segment table, and then within that table we have two registers, or a two-dimensional vector. No, not two-dimensional vector. A vector of size 2. One is limit, and one is base. So the limit of that segment defines the size of that segment within the logical space and the physical space, the same thing. Now we need to check that offset. Is the offset within that segment within the range of its limit or not? If a segment is only 1 kilobyte, if the user space is trying to access an offset of 2 kilobyte within that segment, it's off its limits, right? So if it's not within the range, trap it. If it is within that range, then we're going to read the base address of that segment within the physical memory, add the offset to it, and then access that address directly. Again, this is happening in hardware. These are not like, add instructions or anything. All happening in hardware. So when the operating system is like loading this process, again, it's going to like load the STBR and STLR with these values, and then these will be the registers in hardware doing its job. Okay? Let's see. So this is an example. This is a logical address space. It has like segment 0, 1, 2, 3, and 4. 5 different segments. Now the operating system has allocated these parts of memory to this process, and the segment table holds this. So segment number 0 has the limit or the size of 1000 bytes, and it starts on at this address, right? Segment number 1 has the size of 400 bytes, and it is starting on this address. Where is that? Sorry, this one. Okay. Segment number, this one. Segment number 2 is also like 400 bytes, but it starts at this address, so that's it. Segment number 3 has the size of 1,000 and 100, and it starts at 3,200, so it's here, right? So this table is only be used when the instruction is trying to access a segment, then it's just going to go to the segment table. So this is an example. Let's see and solve it together. So let's say this process has, the segment table, 5 segments with these bases and lengths. Usually this is not happening because, who can tell me why? Why the base is not like at this address? This address is basically wrong, technically. Why? Huh? For example, 4 bytes. Yeah, usually because we said the segment index is the higher bits. They don't usually be mapped into like a byte which is like odd or even not a multiple of 1 kilobyte. Usually they start at round addresses. But theoretically we can still do this, but it's not implemented. So let's say we have like these segments with these sizes. Now what are the physical addresses for the following logical addresses? So if the user tries to access the byte number 100 within the segment number 1, where is that going to be? Go ahead. Tell me one more time. This is what you're going to do. You're going to take a look at the segment table, read the limit and base, check the limit. If the offset is less than that, then add the base to it and then give the result. Okay? So, if you have segment number 1 here, what is this address physical address? The mapped physical address. Alright. Because segment number 1 starts at this address and the length of the segment is 14 bytes, we cannot access the byte number 100 because this is beyond the range of that segment. The segment is only 14 bytes, we cannot access its 100 byte, right? How about this one? That was like an example I showed. How about this one? Segment number 2, byte 0. Where is that on physical memory? What? Yeah, someone said it there. 90, yeah. So because segment number 2 starts at 90, so the byte 0 is 90, right? How about segment number 3, byte number 580? Where is that? Huh? No one? Okay. Yes. It's not able to access. Why? Yep. You've already written code in C. The bytes start at 0. So its size is 580, but it does not. It cannot access byte number 580. It can only access from 0 to 579. All right. So this is a couple of examples. And the sharing of the segments is also kind of similar. So you have a segment allocated on memory, like the editor code, and then that will be just like mapped into both segment tables of different processes. Alright? So we're going to talk more about paging on next sessions. Next session, finalize your groups, and if you are changing your group, just keep in touch, and see you on Thursday. Yep.